So in the previous video we talked about calculating the mass of a compound, which we're going to call the formula mass, when we were given a formula. The question that kind of comes up is, how the heck do we determine the formula in the first place? So in this section we're going to learn some procedures for determining empirical formulas and also molecular formulas. So remember that an empirical formula is the simplest ratio of atom types that are present in a compound, and then a molecular formula is the number of atoms of each type in one molecule of a covalent compound. So we're going to begin with something that seems unrelated to this. So where we're going to begin is with talking about what we refer to as the mass percent of the elements in a compound. So that is, what percentage of the total grams in a sample of matter is of a particular element. Right? So this is also sometimes referred to as the percent composition. So imagine that we have a sample of carbon dioxide, and what we're going to ask is what percentage in grams is carbon and what percentage in grams is oxygen, right? And you put those two percentages together when you have a percent of by mass of each of the atom types that are present. We call that a percent composition. Okay, so relatively straightforward to calculate. What we know is that if we had a mole of carbon dioxide, it would have a mass in grams of the mass of a mole of carbon atoms plus 2 times the mass of a mole of oxygen atoms. That is, it would have a mass of 44.009 grams for 1 mole. We also recognize that in this 1 mole, the carbon atoms would weigh 12.011 grams, and the oxygen atoms, which we have 2 moles of, would weigh 2 times 15.99, or approximately 32 grams. So, given that information, we can go ahead and calculate the percentage carbon that's in the compound and the percentage oxygen that's in the compound. So this is going to be the mass of carbon in 1 mole divided by the mass of 1 mole of the whole compound times 100. So this would be described as being 27.292% carbon. Then if I wanted to calculate the mass percent oxygen, it would be the mass of oxygen in 1 mole of the substance divided by the mass of 1 mole of the whole substance times by 100. And that works out to be 72.7008. And if I add those two numbers together, I'm going to get 100% because there's only carbon and oxygen present in the compound. So you can always do that as a little check. There are a lot of online calculators that will do this for you. You just have to be cautious to enter the formula correctly. So the general procedure for calculating the mass percent of a given element in a compound is you take the atoms of that, the number of atoms of that element in the compound, and you multiply it by the mass of that element, and then you divide that by the mass of the whole thing and multiply it by 100. So if I wanted to know the mass percent sulfur in this compound, I can see that I've got 1 sulfur atom, and from the periodic table, every sulfur atom has a molar mass of 32.07 grams per mole. And then I've got to divide that by the mass of the whole thing. So I've got 2 hydrogens plus 1 sulfur plus 4 oxygens. And then finally I have to multiply that by 100. You should always get a number that is less than 100 for any of these mass percents, and this works out that it is 32.694% sulfur. Okay, so how is that related to empirical and molecular formula? Well, we're going to begin developing that idea now. So we know that the empirical formula of a compound is the smallest whole number ratio of the elements that are present in that compound. Now, this is not always the same as the molecular formula of a covalent compound, right? You need to be aware of that. So for example, if I have the molecular compound water, the molecular formula, that is the formula that describes the number of atoms in one molecule, is the smallest whole number ratio of the elements in that compound, because you can't simplify a 2-to-1 ratio any further by dividing by a common multiple. So sometimes the molecular formula and the empirical formula are identical. But if I look at this guy, hydrogen peroxide molecules have 4 atoms connected in this pattern. What I can see is that the molecular formula could be turned into an empirical formula by dividing by the common multiple of 2, but and they are very different, right? So the empirical formula and the molecular formula are not the same in this case, whereas for water, the empirical formula and the molecular formula are the same. So it kind of depends on the scenario as to whether they're the same. So what we can do is, it's possible to convert from percent composition, that's the mass percent of each element, to empirical formula using the following process. The first thing that we're going to do is we're going to write the masses of each element that would be present in 100 grams of the sample. Now, this is actually pretty simple because it's going to be the same as the percentage, right? So if I say that it is 12% by mass carbon, what I really mean is in 100 grams of sample, 12 grams is carbon. That's what this means, right? So what I'm really saying here is you're just going to replace the percentages that are given with the symbol for grams. Okay. The next step in this process is to then convert those grams present in 100 grams to moles present in 100 grams. So you're going to convert the mass of every element to moles. And we know how to do that. The number of moles is just simply equal to the mass in grams divided by the molar mass. So really simple. Now at this point, you're going to get a bunch of numbers that are pretty ugly. You're going to get one of these numbers for every element that's present. And it's not necessarily going to be obvious to see what the ratio is of the different atom types. So the easy way of doing that is you're then going to identify the smallest of these guys, the smallest of the number of moles, and divide all of them by that. And what will happen there is that the one that is present in the smallest amount, that'll get reduced to 1, and everything else will be a number bigger than 1. And at that point, hopefully you can identify your mole ratio. Okay. Now sometimes your mole ratio comes out very obvious. You'll see that you'll have like 1 oxygen for every 2 hydrogens, and so therefore you will know that your formula is H2O. But other times you'll get ratios where you have something like 1.5 to 1. If that happens, what you have to do is multiply everything that is present by a whole number in order to get the smallest possible ratio of the components. So in this case, we're going to multiply everything by 2, and then our ratio would become 3 to 2, right? So we would have a formula that would be something like this, A3B2. So some little hints here is, first of all, this step often isn't needed. If your ratio involves a half, like in this case, generally we can get rid of a half by multiplying by 2. If your ratio involves a third, or if your ratio involves 2/3, we're generally going to multiply by 3 to get rid of it. And then, a quarter, we're going to multiply by 4, right? And then if it's a ratio that involves 0.2 or 1/5, we can multiply by 5. So, whether you need to do this or not, depends on the particular situation. I'll go through a couple of examples to show how we apply Rule 4. So here's an example. It says an unknown compound containing carbon and oxygen. They're going to analyze it and they find out that it is 27.292% carbon by mass and 72.708% oxygen by mass. What is its empirical formula? So the first step is to write out the grams of each thing that would be present in 100 grams. So this is just going to be 27.292 grams of carbon, and then I do one line for each, and then 72.708 grams of oxygen. Right, so that's step 1, pretty easy. Step 2 is to convert each of those grams to moles, and to do that we're just going to divide by the molar mass, right? Just like that. Okay, so the step 2, convert the mass of each of the elements to moles. So I'm just going to divide each of those numbers by the molar mass. And so here I am. I've got the moles of each of these two components. Now, if you're sharp, you might be able to see that the carbon and the oxygen are in a 1:2 ratio, which means that the formula would be CO2. Now, if you can't see that, what you're going to have to do is step 3, which is where you divide by everything by the smaller of these two numbers. So 2.27 is smaller than 4.54. So I'm going to divide by 2.2722, divide 2.2722. And so when I do that, what I can see is that I get 1 mole of carbon for every 2 mole of oxygen. All right, and these are going to give me my coefficients in my formulas, right? Now, CO in a 1:2 ratio, it's already the simplest whole number ratio, isn't it? So I don't actually need step 4 in this case. Step 4 was convert the ratio obtained in 3 to a whole number. So I would have to do this if I had something like 1 to 1.5. Well, let's do a different one. Let's do this one. 1 to 1.2. It ends in 0.2, so I'm going to multiply everything by 5. And so then that would be 5 to 6, right? So then it would be C506, you see. But we don't need to do that in this case because our ratio at step 3 was a nice whole number ratio. Okay, so here's a real world example. Glycol aldehyde is a compound that is sometimes found in meteorites, and it's of interest because it's a building block of living organisms. So when a meteorite falls to Earth, often scientists will look for the presence of glycol aldehyde. It's an interesting compound for astrobiologists. So what we know about glycol aldehyde is that it has this signature proportions of the elements. It's 40% carbon by mass, 6.71% hydrogen by mass, and 53.28% oxygen by mass. So let's look how we can turn this percent composition data into an empirical formula. So the first thing that we need to do is rewrite these percentages as grams. So that's going to represent the grams that would be present of each of these things in 100 grams of glycol aldehyde. So in 100 grams of glycol aldehyde, you'd get 40 grams of carbon, 6.71 grams of hydrogen, and 53.28 grams of oxygen. Now, then our second step was to convert each of these guys to moles. And I'm just going to use the little shortcut here. The number of moles is the mass on the molar mass. And so here I go doing that. 40 grams of carbon divided by 12.01, that's the molar mass of carbon from the periodic table. I've got 3.3 moles of carbon in 100 grams of the substance. 6.71, that's the grams of hydrogen in my sample, divided by 1.01, that's the molar mass of hydrogen, so 6.60 moles of hydrogen. And then finally, the mass of oxygen divided by the molar mass of oxygen gives me the number of moles of oxygen in 100 grams. So at this point, I might be able to see that the ratio is of carbon to hydrogen to oxygen is 1:2:1. to 1, which would mean that the formula would be CH2O. Now, if I can't see that, what have I got to do? I've got to find the smallest of these numbers and divide everything by it. So the smallest of these three numbers is 3.30. And so I divide each of them by 3.30. And sure enough, I got what I mentioned before, 1 to 1. So what that means is the empirical formula of glycolaldehyde is CH2O. Now, what do I know about glycolaldehyde? What I know is that it is molecular. It's a molecular compound. So the empirical formula might not be the molecular formula. But what I do know is that the molecular formula is always a whole number multiple of the empirical formula. So the molecular formula is going to be some multiplier of the empirical formula. Now n could be anywhere between 1 and any positive integer, right? So how am I going to figure out what n is? What more information do I need in order to determine n? So what I know is that if this is not the formula, right, then my molecules contain more than like just the 4 atoms there, right? More than just the 4 atoms there. They're bigger. My molecules are bigger than just CH2O, right? There are multiple of that. Or another way of saying that is that the mass of one molecule of glycolaldehyde will be greater than the mass of 1 carbon plus 2 hydrogens plus 2 oxygens. So what I really need to do is to measure the mass of one molecule of glycolaldehyde and then compare that to the mass of that I would calculate using the periodic table for CH2O. If it's bigger, I know that the molecular formula is different from the empirical formula. So what I've got to do is measure the mass of one of these molecules, and there's a way of doing that. It's called mass spectrometry. So there's a couple of ways that mass spectrometry can be done. What I'm going to do, what I can do in one of the ways is I can take a sample of my molecule and then I knock off or add some electrons so it ends up with an electrical charge. And then I send my sample through a slit, so I get a nice beam of it. And then what I do is I make I set up 2 plates and they have opposite charges. And what this does is that anything that has a positive charge will be repelled by the positive plate and attracted towards the negative plate. So it gives everything a little bit of a push. So that means all the stuff that comes through here is attracted to the final plate, right? Has the charge that is opposite that of the final plate there. So I end up with a beam of particles, a beam of ions, in fact, that all have the same charge, that are all given the same push or acceleration, moving along what we call the flight path. And what's going to happen is they'll separate out according to mass. And the little ones will travel faster, right? Remember how gases move? The light particles at a given temperature will travel faster. And the heavier ones will travel slower. So if we have a mass marker in there, like some carbon-12, we can use the time that it takes to move along a given path as a measurement of the mass. And so this is referred to as time of flight mass spectrometry. Now, your accuracy just improves as you make your flight path longer and longer. Okay, so it's kind of like a running race, you know. It's convenient to have people run the 100-meter race in a straight line. But by the time you get up to the 1600 meter, running race, you need a really, really big stadium, right? It gets kind of impractical. So what we can do to extend our flight path is make our particles travel in a curve. And this is called magnetic sector mass spectrometry, because we use a magnet to steer our particles in a curve. And so it's kind of like, if you imagine a racetrack and you've got a little zippy sports car up against a big semi-trailer, the light particles can make this curve very well, but the heavier particles, they're harder to turn and they don't make the curve as well. So in this case, what happens is the particles, as they move along this flight path, they spread out sort of horizontally according to their mass. So once we've got the mass of this, whether we use time of flight mass spectrometry or magnetic sector mass spectrometry, we can combine that with the empirical formula to see whether the empirical formula and the molecular formula are the same. So if we measure the mass of one molecule of glycolaldehyde, we see that it has this mass here, 60.05 AMU. So how does that compare to the mass of the empirical formula? If it's the same, then that means that the molecular formula and the empirical formula are the same thing. If it's heavier, then it means that the molecular formula is a whole number multiple of the empirical formula. So what's the mass of the empirical formula? It's 12.01 plus 2 times 1.01 for the hydrogens plus 16. So what does that come out to be? It ends up being about 30.03. 30.03 AMU. 30.03 AMU is not the same as 60.05. So in this case, the empirical formula and the molecular formula are not the same. So how many multiples of the empirical formula do we need to get one whole molecule? Well, you can probably see it, but what we're going to do to get that multiplier is we're going to take the molecular mass and then we're going to divide that by the empirical formula mass, which when we do it in this case, we get 2. Okay, so we know that we got to multiply everything in our empirical formula by 2 to get our molecular formula. Okay, so it's another step in the process, but it's pretty simple. Once you start doing these, you'll see that they're all done the same way. Okay, so what we learn is that we can take percent composition data, use that to generate an empirical formula, and then if we have the mass of one molecule, we can determine whether our empirical and molecular formulas are the same or different, and if they are different, we can then determine what the molecular formula is. Okay, hope you found the video helpful. See you next time.